Problem number 3 on exam 1. Okay, you've got an incline, you're pushing a block up it, and that block has another block just above it. It's being pushed up by the contact force between the two blocks. So the pushing force is horizontal, the incline's at angle theta, and Schottner wants me to solve this systematically in part A, going after the acceleration of the blocks first. Systematically means I better draw a free body diagram, and let me just draw my incline. It's at angle theta, and I've got these two blocks, each of mass m, and I have a choice to make about what my system is. Now let's see, we've seen two block systems before in class, in lecture, and in problems, and since I'm after the acceleration, they accelerate together. I'm thinking it might be wise to define my system as both blocks together. Okay, what are the external forces acting on the two blocks? Well, there'll be gravity down, 2mg, it's acting on both blocks. The horizontal force is an external force, that's pushing horizontally, that's F. And I got to pick my coordinate system. And normally for inclined planes, not always, but normally it's going to be wise to pick my x direction along the plane and my y direction perpendicular to it. And I'll just arbitrarily pick plus x up the incline. So that's the first step in solving this systematically. Actually, since I have this tilted coordinate system, I know I'm going to have to break the weight or force of gravity into components in those directions. So let me just go ahead and do that and draw my little triangle again for the incline and say that this represents 2mg down. I need a component along the incline and perpendicular to it for the x and y components. If this angle is theta, then this angle is 90 minus theta, and that angle is theta. So this component along the incline is going to be 2mg opposite over hypotenuse, or sine theta, negative because it's pointing down the incline and my positive is up. And this component is going to be 2mg cosine theta, but also negative because it's pointing in the negative y direction. So now I'm ready to solve my system. The next step is to apply Newton's second law. The sums of the forces equals ma. It's a vector equation, so it has both an x and a y equation. In this case, there's no friction, so I don't really care about the motion perpendicular to the plane. So I'll just start right off with the sums of the forces in the x direction. And that's going to be F. Got to break F down to its components too. So if F is horizontal, okay, then I will need to break it down into a component perpendicular to the plane and parallel to the plane. If this angle is theta, hopefully you can see that from a high school trig formula, that this angle is also theta. So the horizontal component will be F cosine theta. Okay. We already know that the component of gravity in the x direction is a negative mg sine theta. Those are the only two forces in the x direction. Those have to be equal to the acceleration in the x direction. That's the only acceleration there is, so I'll just label it as A. And then I can write the acceleration equals F over 2m. Oops, I wrote m here. It's actually 2mg. The acceleration is equal to, and also this is A times 2m, mass times acceleration. So the acceleration is the force divided by 2m cosine theta minus g sine theta. Okay, that's actually the answer to part 1. We're done except for thinking. The problem suggests you do a little bit of thinking. Check the answer for theta equals 0 degrees and 90 degrees. Well, at theta equals 0 degrees, A equals F over 2m. Because cosine theta is 1, sine theta is 0. That makes sense. It's just like it's pushing a pair of masses to the left on a horizontal surface. For theta equals 90 degrees, okay, in this case, at 90 degrees, the cosine theta term goes to 0, and A equals minus G. And that makes sense. If the plane is actually incline is actually a vertical surface, pushing on it perpendicular to that doesn't do anything. It's frictionless, and the masses just fall with the acceleration of gravity. So I feel pretty good about my answer. Now for part B, what's the magnitude of the contact force between the blocks? Now here, what you should do is readjust your system to be just the upper block, because the contact force between the blocks is an internal force in this system with two blocks, and just cancels, so you'll never find it if that's your system. So I've got to change my system so that the contact force is an external force, and I can do that if I focus on the upper block or the lower one, but the upper one looks like it's going to be easier for me. Okay, so now we have the sums of the forces in the x direction on the upper block. Well, the forces again are mg down. Now it's a contact force along the plane. Remember, this is actually coming from the lower block. I'm just drawing it here. Okay, and I'm still going to use x and y. No need to change that. So the sums of the forces in the x direction, well, the normal force lies along the plane. That's acting on my system as an external force. The component of gravity pulling down now just one block, so m instead of 2m, is mg sine theta. Okay, just like it was 2mg sine theta here, now it's just acting on one block, so minus mg sine theta. And this equals mass times the acceleration, or ma. So now, what do? I'm trying to solve for n, but I've got two unknowns, n and a. Everything else is presumably given, but I've got a from up above. So all I have to do is plug that in here, and I can say then that so plug in a from above, and I can say that n minus mg sine theta equals the mass times f over 2m cosine theta minus g sine theta. That's just all a from up above, okay, which is equal to, I'll just simplify this, the m's cancel, f over 2 cosine theta minus mg sine theta, or notice that we have mg sine theta here, or minus mg sine theta on both sides. Those cancel. And so I have the result, the normal force equals f over 2 cosine theta. Okay. Well, now let's again do the check that was suggested, 0 and 90 degrees. If you have theta equals 0 degrees, normal force equals f over 2. This suggests that half the push, if the plane is horizontal, half the push goes into accelerating the first mass and half goes into accelerating the second mass. That's nice and symmetric and feels right. If theta equals 90 degrees, okay, then my answer goes to 0. There is no normal force between the two blocks. And that makes sense too if these are on a vertical surface, and I'm just pushing on the lower block with my force F. There's no reason, and they're both just falling down with an acceleration g. There's no reason for a normal force between them. So again, I feel good about my result. So I'm done with problem 3.